So time and frequency characterization. So this chapter is dedicated that we try to use what we have learned before. So we talk about that the importance of phase. We have talked about the amplitude normally. However, phase is also important because by fixing amplitude but by changing phase, we can make totally different, totally distorted signal by simply change the phase. That's the thing going on here. So in continuous time, we define them as like this. So if you remember, input system response will be the output in time domain. xt convolution ht equals yt. If you do the convolution to frequency, convolution changes to amplification, multiplication. So they become multiplication of x, which is input signals Fourier transform, h, system response, which is ht's Fourier transform, which is y, this output's Fourier transform, which is given by this relationship. And the amplitude of this one will be given as, if you put absolute of this, they were given like that, and they can separate like that. They will give amplitude. And the phase, which is given like this. So if you take a look at that, if you happen to have h, you can think them as h j omega and e j omega e j phase of it. Because I think I mentioned that before, any arbitrary complex signal, say a plus bj, you can think them as, this is easy one, everyone knows it. Alright, and then you can think in this way, right? And this one becomes your amplitude, so absolute value of this. Say this is x. So absolute value of x will be this. And this is what? This one can be considered to be cosine theta, and this one can considered to be sine theta. Because when you think about triangle, having theta over here, a, b, cosine theta will be looks like this, sine theta will be looks like this, right? And then this the thing inside here that now can transform to be cosine theta plus j, right? So because of it, let's use this one to be applied to this here. So this one is also a complex number. So assume that they also have now C and D, for example. So when you do that, let's still use A and B for analogy purpose. Is amplitude. Now we can consider them as, to be there as, is amplitude times cosine theta plus j sine theta. That's how we can show our complex number. Those theta, we can consider them as phase h j omega. Those are phase, right? Let's say the single layers of those are phase. Then we can show them easily that they were given by E J theta, right? And then you can think them as, okay, here is amplitude E J phase of H. So from here, this won't come out. If you know its amplitude, its phase, then we can recalculate what is H. Based on this simple calculation, simple process you already know about. So that's the reason. Actually, the phase over here, we just define those theta to be our phase. Just define theta to be our phase. So this amplitude is a phase. This is how we represent our H. Before we move on, any questions? No. So our amplitude, which is y, those are given like this. Amplitude of this will be what? Amplitude of this and amplitude of this. Because if you think about this relationship, y, which is y amplitude times E j phase of y, equals h times x. So amplitude of h, E j phase of h multiplied x, E j phase of x. That's what we are talking about. And then this representation, it makes sense. I did not put j omega, just put h and x. And then this amplitude, so h times E j phi h times E j phi x over here. And this one becomes E h times phi x. Because of this relationship, amplitude of y, which is given by this, phase of y is given by this. So if you see this, amplitude become multiplication, as you can see over there. Phase looks like it's added together. That's the reason that it looks like this. From this relationship, if you compare y and x is the input, y is the output. How the relationship go? How is their relationship? First of all, in case of amplitude, y is x multiplied by h. So h, we can consider them as a gain. So assume that you have a system, you have an input, you have an output. Oops, I'm sorry. Reversed. Input, output. Amplitude of output will be multiplication of h to the amplitude of x. So this one will be gain given by the system. In case of phase is what? Phase of y is shifted by delta h. The original phase, the maybe 40 degree, for example, plus 10 degree shift, the phase moved. That's how you can see over here. So that's the reason people say this is a gain, which is the multiplication. This is a phase shift, basically addition. In case discrete time, this is continuous time. Discrete time does not change much because in case of discrete time, they only change j omega to e j omega, but same principle, same form, still exist, so it does not matter for this. So that's phase and amplitude and how their relationship goes. In case of here, what if the phase is linear? What if its phase is nonlinear? What happens? Somebody may ask. Before we go to here, what's the meaning of linear? Of course, you are familiar with the case that the system is linear. Say, y equals xt times 3. This is a linear system, right? You may be familiar with these kind of things. But nonlinear phase, linear phase, doesn't make sense, right? So, one of the things we can think about here is, if this one is 90 degree fixed, this is linear. A little bit, right? We can add them, we can multiply them, multiply and add together, doesn't matter, right? What if this was given by is it linear? What's the meaning of linear? Superposition held or not, that's linear, right? So in linear system, you have two inputs. If you add them together, output of this is same to just have do them individually. That's the meaning of the input, meaning of the linear. So this is linear because our input is W, right? So this is linear. If this one is square, this is nonlinear in the viewpoint of frequency. So if you talk about the linear in phase, they often say they are shown as something multiplied by W plus some variable. That's what we say linear. Non-linear, sometimes omega square, omega triple, those kind of things often say non-linear in this case. So let's have, so keep in mind, phase may be linear, phase may be non-linear. Let's take a look at what happens. The first one over there, figure A, so also come from our textbook. Textbook has a copyright for this. Say this is our input to the system. Say this is input to our system. Well, it makes sense, just arbitrary impulse signal applied to the system. And B is the case that we have a linear, if system has a linear phase, if in case of C, B and C are quite different. Can you say they're the same signal? This and this. This. Are they the same signal? So both B, C are output of a certain system having same input A. But the system response, which is H over there, is a little bit different. So to show them more clearly, let's do this. So let's do this. So assume that in this one is linear, system has a linear phase. Both of them has unit gain, meaning that the amplitude is 1. So unit gain is what? In case of our system, it can be divided into H and phase of H. This H has together unit gain. This phase has some degree to operate. If this is input to the system, then assume that we have a unit gain, so amplitude doesn't change, but system response H1 looks like that. E minus j omega 0 T0. Assume that this is our system response. What is this one's amplitude? 1. What is this one's phase? Minus. So omega T0. This is this one's phase. T0 is constant, right? So it's proportional to omega. Is what? So this one is linear system, right? Linear phase. If you pass through this one, then it will look like this. And if you actually calculate them like that, it looks like this. It's calculated by our textbook. If you calculate them, if our system has something like this, so now it is not like that, but has some nonlinear phase. Then they will change like this. However, when this one's phase is minus omega T0, which is a linear phase. And also, based on our Fourier transform, our x j omega times e minus j omega T0. Then this one will have, you already know that by transform this, t change to T0. When you think about Fourier transform's property, minus omega T0, they change to minus, come out itself, minus T0 like that. So from this analysis, we know that after passing through the system, this input will shift by T0, say T0 is 10 over here. So they shift by T0 and show as it is. And as this linear does not change much. Actually, does not change at all, I'm sorry. If this typo, just go over here. Assume phase, nonlinear phase. Then they are totally distorted. Yes. We have those linear phase and some amplitude, meaning that then they're also distorted. However, so now this is our input. This one go to one system, we have a system response like that, and this is the output of the system. Let's put this one to this linear system, linear phase system, then what happens? This one should shift by T0, we can see here. This one shift by T0, which is 10 over here. So when you can see from this example coming from our textbook, it's like that. Input to the system, from the input to the system, if the system phase is linear, does not matter about amplitude. Amplitude is a unit. Amplitude is basically linear. If the phase is linear, then they basically shift by time. Okay. Remember the previous slide? In previous slide, we talk about that the system compared to input, output is adding some phase, shift in phase. Shift in phase is what? When they start, they shift. So you can see one example over here. Say that every timing go to change to as linear. So they basically moved equally. They shifted equally. So the shape does not change. Also, we can also do in Fourier transform characteristics. If those shift is non-linear, some port moved much, some port does not move much, some port move too much, then signal will be distorted. It's very different from input signal. And even this distorted signal, when they go to linear phase system, they function similar. Even though this is distorted signal, they shift by phase. That's what they talk about. So this one is another example showing that phase is important, as you can see in the previous example. Phase is very important, not only the amplitude, and also in case of linear phase, input and output is kind of correlated. But if it is a non-linear phase, then the input and output may be not correlated too much. How about in discrete time? We do the same thing for continuous time and discrete time. In case of discrete time, we have original signal. If you have linear phase, then they shift by 5. In this case, they put 5 as a t0 over here. So in case of there's a linear phase, they just shift in time without changing it. System is nonlinear. Nonlinear means nonlinear phase in this case. The gain is still 1. This signal and this signal is totally different. So not only continuous time, but also in discrete time, when you have nonlinear phase, then the signal is quite different. So not only the phase is important, but also if you have linear phase system, then they only have slightly change in time, doesn't matter much. But if you have non-linear phase, then you will have difficulty to finding what is input and how to control the output. So any question by far? So remember, linear phase doesn't change our original signal, just shift by time. So linear phase can be interpreted as shift in time, as you can see in the previous two examples. And the amount of time shift, how much they move, determined by phase law. What's the meaning of it? So in here, let's go back to our previous example. In here, we put example like this. Then they shift in time like this. If you have this one, then they shift like this. Meaning that if your phase is minus omega 0, in time domain, they shift like this. Meaning that if you plot those phase if you plot those phase by our variable omega, omega is on our variable. This one can be interpreted like this, minus t0 times omega. So if you think about the slope x and y, this is what? Slope. If you plot it x and y, those two are the slope of the relationship. If you see the same relationship, this phase of h is our y, omega is our x. So minus t0 can be considered to be their slope. If you know those slope, then we can know how much they shift. If you know those minus t0, you can find how much they shift. So from this relationship, in case of continuous time, which is shown in here, they delay by t0 in time domain. Meaning that the slope of this relationship determines how much they shift in time. Likewise, in continuous time, this only t0 change to n0, which is this is t0 corresponding to n in discrete time, delayed by n0 in time domain, which is the same relationship. So, in case of time shift, how much they move in time is determined by slope of the phase. That's how you can see it. So we introduce a new concept, say group delay. Group delay is given by, let's say, this is what? This is the slope, right? This is the angle that this is this, right? And typically they given, probably in this case, they given by minus t. And we add minus here to make this one plus. Because this one is definition of group delay. How much they delay in group. So if you go back to our example, if you talk about the linear phase system only, you can consider this as this is starting from 0, but they're starting from certain point over here, and they become peak at 0. This one starting at a certain point here and become peak at 10. So we can think that this is delayed compared to this. This one starts and then this one starts later. That's how we see it. So we can think that this one, after passing through the linear phase system, they are delayed in time. That's what we have learned by far. But in case of linear system, all points in this shift together. Like a group of those points move together. So we can think that those group is delayed in time together like this. That's the reason we call them as group delay. Group of signal, group of point, they because of linear phase system. And then how we define how much they are delayed by using the slope. The slope. However, from the Fourier transform, if you have this, it was shown like this. So this is delay in time, delay by t0, right? However, after calculating those slope, they given like a minus t0. So we want to remove this minus to match them. That's the reason we put minus over here. That's the only reason we put the minus over there. So group delay, which is defined like this, they defines, especially the case the linear phase system, they decide how much they delayed in group. That's what they say. What about nonlinear phase system? We don't know, right? We don't know. We don't know what happens. They shift in time, but they shift in different ratio, so we don't know what happens. So this one typically defines only to linear phase system, because in nonlinear system doesn't have much value to do it. So in case of introduce a new concept, we consider a say they are zero except a certain point. I think it's better to show some picture to have it. Remember, this is output plane, and consider a very narrow band input, meaning that in frequency level center, they are very narrow. For delta, omega plus delta, they are not zero, omega minus delta, this is omega. They are not zero. So other than that, there's a very narrow, sharp band. Of course, in here you may have something like this. Doesn't matter, but this is an example. You can have it. And this one, we can approximate it. We can approximate this one's phase to be like this. We can approximate this one's phase that they are omega 0, alpha, minus some phase. So our system output what looks like y j omega, roughly say x j omega times amplitude of h times exponential minus phi minus what I'm saying. J is missing over here, so J over here. So on here we assume that the system response has a phase of, assume that this one has a linear phase, so it has some linear phase, right? This is linear in frequency, and add some more phase just in case we have some more shifting in time more. So that's what we assume. So we can consider them as like that. Now we assume that. So in here, if you to make you, I think some of you may be confused. This is X, which is input system. This is H, which is the system response. And we assume a linear system response. In case of linear system, linear phase in the system, that means the phase of H is linear, right? Linear is what? A times X plus B. Those are the linear system. So let's assume that we have X as instead of omega and alpha instead of A over here, and put phi instead of B over here. That's what you see in here. So this one has a phase like that. Those phase, to show the phase, we present system as E minus J by phase, which is now what I'm talking. The phase were given like this, right? So if you represent them, they were given like that: EJ minus alpha omega minus pi, because of the phase. That's what you can see over here. Okay, so you can represent like that. And you can think them in here, you can also divide them like this. From this one, when you see the viewpoint of x input, y output, what can you see it? What can you see? Because this is what? And this is what? If you only see the amplitude first, let's divide by amplitude and phase. Amplitude of this system, well, how much amplitude of x changes after passing through the system? This is amplitude of itself. Amplitude of h is what? Amplitude of h. Amplitude of this one is what? How much? What is amplitude of E minus j pi? What is amplitude of it? 1. This one is what? 1. So the change of this one's amplitude will be h. 1, 1. So h. What they see over here, magnitude changes by h, amplitude value of h, and there will be some complex over here, because then we can think them as they delay by like this. But there's one trick. You may have to be very careful on this, because if you see this, what is it? Right? Their ratio, the absolute value of this one will be the same. However, because of the phase, actual amplitude y, this is 1. Does not matter. However, if you consider them in time domain, assume that you have amplitude of this. After passing through the system, they will look like that. So if you select a certain point, delayed by phase pi, if you point of time, actually their amplitude changes because of shift in time. So that's what I'm talking about. They will be looks like, because of multiplication complex, that they may be shaped a little bit. Also, we will have a time delay over here. That's the reason they look like that. Before we move on, questions? So, one thing you have to remember two things. One is, in case of linear phase, they can be considered to be delayed time. To solidify the equation, we define a new concept called group delay. So, let's have an example. This is come from our textbook, so copy go to our textbook. The first thing you can see from the example is what the hell. So, do it one by one. First of all of these three graphs, they have frequency. Of course, they are plotting in frequency. So let's try the first one. The first one, And second one, both of them are shown in phase. And third one is group delay after calculating those phase. So if you see this from this graph, what can you see from the first one? Well, basically phase is quite flat, except this point, and this point, right? So let's think about what they are. Over here is roughly say 50 Hertz. Over here is roughly say 150 Hertz. Over here is roughly say 300 Hertz. Actually, this is the output, the result of plotting the phase of each system. This system, what is meaning of this pi? Sigma is what? Multiplying and addition, right? Not multiply. How about this? What does the symbol means? What does the symbol means? K. That means A1, 2. What's the meaning that AK equals 1 to 5 for this? Right. So A equals 1, 2, 3 multiply until 5. There's a symbol of it. So here we have three systems in form. The form will be given by 1 plus j omega divided by omega I squared a delta I by omega I, and say minus plus going to these values, certain values like this. We have three systems. One, omega 1, 2, like 3, and 3 of these are multiplied like this. That's the system we are talking about. Okay, can you? Okay. So, in case 1, we define them like this. Omega 2, we define like that. Omega 3, we define like that. Corresponding values of chi is given like this. If you plot it, it looks like this. It looks like that. And because of it, we can calculate this 50. Because 50 corresponding to omega 1, pi is close to this. 50 times 2 pi close to this. So you can see over here. So from this example, you can plot it individually, and then you can see that how it looks like. From this calculation, you can calculate the group delay of each of it. So if you see this one, if you see the group delay, what is the group delay? Group delay is slope of the phase. Slope of the phase. So group delay is slope of the phase. And you can calculate the total phase by adding each of it. Can you get it? So you first plot them, add the phase of each H1, phase of H1 plus phase of H2 plus phase of H3, then they will give you the total phase. And then you can calculate the delay. which is shown in here, and then you calculate the delay looks like that. Because if you unwrap it, there will be edge which looks like edge like that. And then the slope, in this slope, this slope is almost zero. So slope over here is flat, except those changing period. In changing those period, they are having slope of minus, and in the group delay, slope becomes slope of plus. So they become positive over here, and slope of minus over here change to positive over here. Of course, this slope is less stiff. This is very stiff, falling very sharply. This one is less stiff. This was even less stiff. So the amplitude of the slope is smaller in here, larger over here. That's the reason they look like this. So this is unwrapped phase after calculating the whole total phase, or calculating from each of it, and then after doing the derivation of that, you can calculate the group delay. So in group delay means what? So to talk about long story short, what's the meaning of this group delay? Group delay has a characteristic that how much the input signal is delayed. So what's the meaning of this one? Group delay means how much they are delayed. If group delay is 0, that means input comes out as itself. There's no delay. Is it right? Ideally, of course. What this one says here is, if the input, we did not change the input yet. Now, if input has certain frequency, they may be jammed, they may be delayed. If input is DC or say 10 Hz, for example over here, the group delay is 0, and no delay. So input comes, output comes. If the group delay frequency happen to be 150 Hz, then group delay is about 0.06 second. So they delay by 0.06 second. So when input comes, then output wait, and after 0.06 second, they comes. What about this? If they happen to be 50 Hz, then 0.1 second. When the input comes in, output is even more delayed, and it comes after 0.1 second. That's what this group delay talk about. Group delay, in short, they talk about how much the input signal, the total group delayed in time. They depending on the slope of the system response. Actually, the minus is in there. And then what this example shows in my textbook is depending on the frequency, depending on the system. The system has certain they have a system response of frequency, and depending on those frequency, there is huge delay happens. And depending on the frequency, the amplitude of those delay is different. That's what this example shows. So now, because we talk about that, we can represent a complex number by amplitude and phase. And also, we talk about that, and also we talk about that we can giving phase is important, and if you have linear phase, we can calculate a kind of group delay, because those slope in phase we can represent it as a delay in time. So what about, what shall we do it? We now introduce a border plot, which you already know about it. And now, before we reach here, I gave you several reasons why border plot is important, why we are drawing border plot. border plot is one way we can represent the system. Of course, we can represent system in many other ways. However, first claim we have by far is what? We can represent a complex number by amplitude and phase. So if you know amplitude and phase, we can know the system. So that's the reason we have border plot. Second, we want to know the phase. Phase is very important. So from this graph, you can calculate. Actually, we can see how the phase looks like. Claim number 3, the slope, the delay in time is given by the slope in the phase. So from the border plot, you can calculate the slope of the phase. So what you can see from here, this is the simple thing you often see in your low-pass filter. You will have a certain frequency, or certain frequency, they are flat, and then they go down. That's what you can see over here. However, in case of this, the phase, when you plot it, the slope of the phase is flat over here and flat over here. So those one doesn't have a delay. What about here? They have a delay. So there's a slope. So from the slope, we have a delay. What happens? That means we only care about the amplitude by far when you talk about the circuits, when you talk about those dynamics in the mechanical system. We do not care about the delay much. We only care about the amplitude usually. But this one tells you that if you have certain frequency, there may be no delay. If you happen to have certain frequency, there will be some delay happens. That's what this one graph talk to you. That's the reason that we are learning how to plot. So let me speed up a little bit from here, because I think that most of you already know the border plot. Border plot is you basically draw it. You draw amplitude and phase, and you plot log 20h to get amplitude, and then angle of it to be a phase. Because of it, this phase was often given by minus pi to pi or 0 to minus 2 pi, those ranges. And now, because there's 20 over here, we introduce a new concept called, I think that's type 10, right? That's 10, I'm sorry. We describe decibel. Decibel means 20 times log 10, that's decibel. So because we have 20 log 10 over here, 20 log 10 over here, when you change 1 at y-axis, that means they change by 1 decibel. That's what I'm talking about. So that's it. And I think you just draw the plot, solved many problems before. Now I'm talking about the reason we are using border plot, because we can represent the complex signal using the phase and amplitude. That's what we're talking about. This is a very special case, because if xt is real, this one amplitude is even function of w, and this one is odd function of w. If this is real, then this is odd function of w. What's the meaning of the odd function? Right, reversed. So if omega, this one is omega, it's positive, for example. In negative omega, this one becomes negative. Even function is what? Omega is positive, this one is positive. Assume that this omega is positive, this is positive. If omega is negative, then this one is also positive. That's what you're talking about, even other function. So basically, if we already know one of these, then we don't have to know negative omega, because we only care about positive omega if xt is real. Because omega is positive, then we can calculate this. Omega is positive, we can calculate that. if omega happen to be negative, we can calculate this one because they were the same. If omega is negative, then this one can be calculated because there will be minus of this when this one omega is positive. So we don't have to calculate the negative omega case in this because we can calculate, we can deduce from positive omega cases because it's even and odd function. That's the reason it only cares about positive omega. So let's plot it. In both plot, discrete time is not often used. They are not often used because they are not so advantageous compared to continuous time. Why? If you plot, let's go back to Fourier transform's characteristic. In case of frequency, after transformation, in frequency, continuous time Fourier transform is continuous in frequency. They are periodic in frequency. No, right? If in discrete time Fourier transform, they are periodic in frequency. I see some of you have question marks, some of you have those. So in case of Fourier transform, continuous time Fourier transform meaning the continuous in time, discrete time Fourier transform meaning discrete in time has different characteristics when they transform to frequency. Continuous time Fourier transform, which is continuous in time, in frequency they are continuous and non-periodic. Discrete time Fourier transform, when you transform discrete time signal to frequency, they are continuous in frequency and periodic in frequency. Oh, in the case of discrete time, when you go back to the previous case, which is continuous time, both plot, they will have like this, which does not repeat. This is not periodic, so it does not repeat. In case of discrete, they repeat because they are periodic function. They repeat in frequency. So they just keep on repeating. So where to cut? Where do we see? This is band pass filter. This is low pass filter. This is what we don't know. So that's the reason that we does not use both plot often for discrete time signal, because discrete time signals Fourier transform, they are periodic in frequency, which is they keep on repeating, so it doesn't have much meaning for both plot. Right. That's what we say here. This is periodic, so we don't care about that much. If you reuse it, as this is periodic, and we know that this is even function and odd function, so we don't have to worry about the minus in this case. So we assume that we have a period, as this is a period signal, we care about one period which is pi, minus pi to pi. But as this is even and is odd function, so we don't have to worry about the minus. So we only care about 0 to pi in this case. So in case of discrete time Fourier transform, border plot, we don't care about, actually they looks like this, but we don't have to care about minus, we don't have to care about other than the period. So we only think of only the area which doesn't have much meaning to us.